All right, so the first part of today's lecture is a little bit of a continuation of last week, but now we're going to talk a bit more about the products of explosive volcanism. Last week we talked a lot about the processes involved, like what's causing them to go bang, and now we're going to look at what forms, and as geologists this is more what we're going to be looking at in the rock record. You guys also saw a lot of this in last week's practical. Sorry about that, the timing of the lectures and the practical just didn't quite work out how I wanted it to. And after that we'll talk a bit about volcano morphology and landforms and how they relate to different tectonic settings. All right, so we'll start with volcaniclastic rocks. So last lecture we talked about how explosive eruptions fragment the magma into clasts. And in general, the more explosive an eruption, the finer it'll fragment it. So if we have a very, very explosive eruption, we end up with ash. If we have something a bit less explosive, like a Strombolian eruption, then we end up with these Scoria, bombs, and lapilli that are a bit bigger. Volcanic clasts are kind of similar to the sedimentary clasts that you would have worked on. They're just divided by size. So bombs are anything that's bigger than 64 millimeters in diameter. Lapilli are between 2 and 64, and ash is less than 2. And there are subdivisions within this, like there's fine ash and coarse ash, but I think we can just learn these sizes and that's good enough. Similar to the sedimentary stuff, it is a log 2, so you can see lapilli 2 times 2 times 2 times 2 times 2, and you end up with 64 millimeters. That's the top size, right? And when you get an explosive eruption, there's two ways that clasts can be dispersed. The first one is that they fall out ballistically, and this means that they fall in a parabola. Ballistics, like when you're shooting an artillery or something, that the Russians and Ukrainians have been doing a lot of recently. It's got this nice parabola as it falls. The smaller clasts basically end up in a volcanic plume, and they end up spreading out in the upper atmosphere. And then they can be sedimented from, just dropped out as they get blown along by the wind. And they can be dispersed over quite a large area. Now, there's two different types of clasts that we can see coming out of a volcano. And these are called either magmatic or juvenile material, and non-magmatic, and these would be things like xenocrysts or lithic fragments and clasts. So the non-magmatic stuff will be chunks of the wall rock from the vent that the volcanoes are erupting through, and these might consist of previously erupted or crystallized material. When we talk about non-magmatic clasts, it's basically the same size division as you have for the volcanic or magmatic stuff. But the largest size are called blocks instead of bombs. So we have blocks above 64 millimeters, lapilli at 2 to 64 millimeters, and ash under 2 millimeters. The kind of blanket term for all this ejected material is Tephra. Now, if we can find a pointing stick. Got a couple of pictures of Ignimbrites that we'll talk about a bit more in a bit, but this is just to show you the kind of range of material you can get. And in this one on the left, it's relatively few lithic clasts. And so there's stuff like sandstones, there's shales, there's old bits of lava. So you can have all sorts of stuff incorporated into these. The one on the right has a lot more lithic clasts, but they're all of this black ignimbrite. Now the host rock is also an ignimbrite, but it's got a different composition, a different color. So just to give you an idea of what kind of material can be in these volcaniclastics. So starting with the finest grain size, I mentioned last lecture that the ash are these fragmented magmatic bubbles. So essentially little chunks of the bubble walls that have been shredded to pieces and thrown up in the air. And you can see in the top left picture, these are a few tenths of a millimeter across, very small, and you can still see the bubble shapes in them. When we look at it in hand sample, it's kind of looks like a dusty powder, depending on the grain size. In general, the grain size and the thickness of a tephra deposit decreases away from a volcano. So close to the vent, you might see lots of blocks and bombs and so on, but those are just falling out from the air in those parabolas. They can only get blown, blasted so far. And what then happens with the ash is that gets brought right up into the upper atmosphere, it's dispersed by the wind, and you get this kind of downstream, like downwind plume of ash cloud, and then that rains out. And you can see here, this is just something called isopack contours. Isopack just means constant thickness. So near the crater, we have over 20 meters of tephra deposits, and as we go out, it goes through 5 meters, 2.5 meters, 50 centimeters, and quite far away, you're still getting 20 centimeters of ash deposited from this particular volcano. Right. So this is really useful because we can actually map the tephra spread of an individual volcano. And you can do that either, you know, if you see the volcano erupt and it happens while humans are around, we can go out and we can literally look at where the ash has fallen and measure the thickness. In kind of prehistory or before humans were around, you can map these out based on composition. So if you can go and find an ash layer and maybe it's got a particular composition or a particular thickness or relationship to other ash layers, and you can map those out to different volcanoes. So this map just shows different tephra deposits from major eruptions in the past million years or so in the western US. And you can see the Mount St. Helens ash. This is the 1980 eruption, which was quite an explosive Plinian eruption. That's the one where the dome collapsed, sudden decrease in pressure, and we get a big Plinian eruption. But it's really kind of piddling compared to a lot of these. This is covering most of the width of Washington State and crossing into Idaho. Mount St. Helens erupted 3,800 years ago, where it was much bigger, ended up going up to Canada. But some of these other ones are just huge. There's the Glacier Peak ash from about 15,000 years ago. Mazama, which is Crater Lake, that we'll talk about a bit later. And then, of course, the big daddy is Yellowstone. And 665,000 years ago, this was enough to cover most of the US in at least half a centimeter of ash. So this is just a huge eruption. Now on the right is showing this kind of tephrochronology, and what people have done is they go in, look at the composition of the ash, and then you can measure it to, say, lavas or like near vent deposits around a volcano. And this is actually in the UK, but you'll notice the names of these layers sound pretty Icelandic, and that's because these are major Icelandic eruptions that deposited ash in the UK, and so you can actually date the soil by measuring the composition of the ash, comparing it to the volcanoes, and you know what date those erupted, either from historical records or using some sort of dating method on the volcano itself. And that's called tephrochronology.
Question?
Go ahead.
It seems like a very, very thick layer to be depositing in England from a volcano in Iceland.
Yeah, so this all depends on like how explosive the eruption is, what the wind direction was, how intense the wind was. So often with these big eruptions, the ash will end up circling the globe. It will get up into the upper atmosphere and it will kind of float around, and you might get very small amounts. But yeah, Iceland too, I can't remember where in Britain this one is, but there's at least a couple of centimeters of ash, so it's probably traveled, what, 1,000 kilometers or so.
But it should be more thicker layer in Iceland than
Yeah. And this one here, Laki, it was a huge eruption. We'll talk about it a bit later, but it was absolutely devastating for Iceland. Yeah. Yes?
I think maybe one of the explanations to why such thick layers were found in England could also be that there's something called the Icelandic low, so there's always very high winds in Iceland.
Okay, yeah. And those could be blowing stuff towards the rest of Europe. Absolutely. Okay, on the bigger side, in the practical last week, you would have seen some Scoria lapilli. Again, it's just purely size defined. So here are some Pumice lapilli about the same size, obviously different composition. And then bombs, we would probably see them something like this in the field. But this is what a bomb looks like when it's just been ejected from a volcano. So I think this is from the 1983 eruption of Kilauea, so back to Hawaii again. But, you know, this kind of glowing mass of magma that's been thrown through the air. Now, we've talked about pumice and scoria a lot in the course, but I just wanted to be a bit more formal about it. Basically, the main distinction is compositional. Scoria is mafic and it's dark. Pumice is felsic and it's light. It might be a bit confusing when you compare it to the obsidian glasses that we saw last week. Now, obsidian, the reason it's so dark is that it's unaltered glass. And with this pumice, because it's shredded into this fine mesh of bubbles and there's all these volcanic gases around, and then it's thrown through the air, it tends to be altered. And so it's kind of like in some of those obsidian, we had cracks where it altered to like a white material. And you can imagine with pumice, it's like the whole thing's been altered. So basically, both glasses might start out darker in color, but the pumice alters white. The mafic scoria, even if it's altered, it stays dark in color. Because of the difference in magma viscosity, there are some other differences. So scoria is denser, it sinks in water. And it's less to do with the fact that basalt is denser than rhyolite and more to do with the fact that scoria tends to have thicker vesicle walls. So the bubbles have a thicker amount of magma separating them. And as far as I understand, that's to do with the fact that when you have low viscosity, you can grow bubbles quite quickly and they can coalesce together, but then most of the bubbles will actually just escape the magma. They'll degas through. Whereas in a pumice, they can't really escape, and so you end up with this really, really fine, like stretched membranes of kind of rhyolite separating these bubbles. So that's why pumice is so light, is there's actually very little rock in there, and it's mainly air. Okay, tuffs are basically ash deposits. They're consolidated, and they're defined by having more than 75% ash in them. You'll also see, because obviously this ash is falling and it might be falling onto an area where there's other sediments, it could be reworked by other sedimentary processes. You'll get mixed rocks where they're mixed between a sedimentary rock and a tuff, and they will be called tuffaceous. So it just means tuff-like, tuffaceous sandstone, tuffaceous shale, that kind of thing. Ash can be deposited and transported in different ways, and that changes the name that we would give to these tuffs. The most obvious one is the fallout deposits. That's this ash that's being carried downwind in your plume from a volcanic eruption, and it basically falls out gradually, and the larger grains will fall out first, and the further away from the eruption you get, the finer grains will fall out. So it's very well sorted. It can fall onto land, which would sometimes be called a subaerial tuff. It can fall into water. It could be a lake, it could be in the sea. That might be called subaqueous or submarine for the sea, or lacustrine for lakes. But not too worried about the subdivisions there. There's also ash flow tuffs. And as far as I can tell, and I found it a little difficult to make this distinction, these ash flow tuffs are basically ignimbrites or base surges that we'll get into in a sec. So these are formed by pyroclastic flows or pyroclastic surges, and they end up looking like a tuff, but we're often going to call them an ignimbrite. And then, yeah, there's rework tuffs. So this could be, quite soon after an eruption. If you deposit a huge amount of ash on the side of a volcano or something, it's very unstable. It can get eroded very easily, and then that tuff can be deposited downstream, downhill, somewhere else as a rework tuff. You can see in the top right corner some of these like ash shards in the tuff, and you can again see that these are little fragments of the bubble walls in the volcano as it explodes. And I just wanted to note that tuffs can look all sorts of colors, and they can be quite weird. So you shouldn't really be using color to identify a tuff, because you'll go wrong. Yes?
Is there a way to tell ignimbrites and tuffs apart?
There is. I will get right onto it. So, yeah. So ignimbrites are basically a special kind of tuff, and they are deposited by pyroclastic flows. Now, I talked to a couple of people in the practical about welded tuffs, and I think welded tuff, to me at least, is kind of a bit of an old school name for an ignimbrite, because the ash is welding together, and that means it's still hot when it's deposited, and basically it kind of sticks a bit. This kind of welding only happens when the temperature is above 600 degrees C, so it can't really happen from one of these fallout tuffs dropping from the cloud as it's blown downwind, because it's just going to be too cold. So to get these kind of temperatures, 600 degrees plus, it's almost always going to be a pyroclastic flow. The picture I showed you before with the different lithic clasts were two ignimbrites, I think from either the same volcano or same volcanic province, but they look completely different based on what they're carrying. And we have these four main components that we talked about in the practical. So there's fine-grained ground mass of ash. There are phenocrysts. These are almost always there, not always. There are juvenile clasts. So these would be pumice or some sort of molten magma that's being fired through the air. They are usually compressed to fiamme because it's still hot when it's being deposited. In some ash flows, you will get chunks of pumice that haven't been squashed so much, and that just means that it had time to cool before it got incorporated into the pyroclastic flow. And then you also see these lithic clasts, or lithic fragments, some people will call them. These are wall rocks to the volcanic vent, or they could be material that's actually picked up in the flow. Yeah. And just to remind you what these pyroclastic flows look like, we have a bunch of different types. The obvious one here is these Plinian ones where the eruption column collapses and then it flows back down the side of a volcano. You can also get these dome collapse, these explosive eruptions that trigger pyroclastic flows. And so yeah, generally Ignimbrites are from pyroclastic flows, and these fallout tuffs are this kind of long distance rain that's coming from the ash cloud. All right. So there's another type of ash flow deposit, and these are called pyroclastic surges. And the deposits that's left usually gets called a base surge. And what this is just before a pyroclastic flow comes down, you kind of get this low density version called a pyroclastic surge. So they move much faster than the high density pyroclastic flow, and it's pretty much just air and ash. And it's doing the exact same thing. It's collapsing down the side of a mountain. It's a density current. It's just faster moving, and it's got less stuff in it. So they're called base surges because often they will underlie an ignimbrite because they happen earlier in an eruption, or they travel faster to get there. So yeah, here we go. This is a picture from somewhere in Italy, I believe, with a very maybe 80s, 90s looking dude. And you can see there's a base surge here, which is basically just fine-grained ash, and above that there's a proper ignimbrite with all our lithic fragments and fiamme and all that kind of thing. You can see clearly visible sedimentary stratification. Usually it's going to be planar bedding or cross bedding, and the type of planar bedding, this is that kind of upper flow regime that Christian talked about a lot in Spain, where it's the very, very high velocity, and you end up with a planar structure. And we saw a really good example of this in Spain. It's actually the opposite way around. There was the ignimbrite on the bottom and the base surge on top. But here you can see the ignimbrite is full of all these blocks of, I think these white blocks were mainly juvenile magmatic material. We could also see phenocrysts, we could see chunks of pumice, we could see lithic clasts. This is an ignimbrite. And above we had this incredibly well stratified base surge deposit that's basically just ash. So these are probably different eruptions if this one's lying on top of the ignimbrite, but I'm not quite sure. And the last type of deposit I want to talk about were lahars. So lahars are a mud flow, kind of like a debris flow of water and pyroclastic material. And if you imagine that you erupt a bunch of stuff onto the side of a volcano, again, it's very gravitationally unstable. If it rains, that stuff can just get swept away. And sometimes these can actually flow hot because the pyroclastic material has just been deposited, and even when it gets rained on, incorporated into a stream or a debris flow, that water can still be really hot. So up in the top right here, you can see an example of one. I can't remember what eruption this is from, but it's steaming. I'm not sure if that's obvious in the slide, but this was flowing at a very high temperature. They move very fast, not quite as fast as pyroclastic flows, but still very, very fast. And some of them can be up to about 100 meters thick. So these can bury buildings, destroy them. They're very, very dangerous volcanic hazard. And once they're deposited, this kind of muddy, tough, hardens like concrete. And this, what you end up with, this is a solidified lahar deposit. But if we found this in the geological record, we'd probably classify this as a reworked tuff. It would look like a tuff, maybe with some other sedimentary grains in there, and you'd conclude that it had been washed downhill and redeposited. All right. So volcanoes erupt both magmatic and non-magmatic clasts. Overall, these are called tephra, and they're grouped by size into ash, lapilli, and bombs if they're magmatic, blocks if they're non-magmatic. They can either rain out from ash clouds or be kind of ejected ballistically, so curving through the air. The grain sizes and the thicknesses of tephra deposits decrease away from the eruption site. So very thick, lots of large blocks and bombs near a volcano, and much, much finer further away. Volcanic sedimentary rocks that are largely made of ash are called tuffs, and when you deposit them from a pyroclastic flow, they're called Ignimbrites. Four key ingredients of Ignimbrite are ash, phenocrysts, fiamme or juvenile magmatic material, and lithic clasts. Does anyone have any questions about that section? Okay. All right. Volcano morphology. So morphology is just a fancy way of saying shape. But I'll probably use those pretty interchangeably. The shape of volcanoes depends both on the eruption style and the magma viscosity. And obviously the eruption style and the magma viscosity are dependent on all sorts of things, including the volatile content, the temperature, composition, whether or not there's any water externally that's being added, like in a hyaloclastic eruption, the magma chamber pressure, all sorts of things. I think this is probably easiest to understand if we just pretend that we have volcanoes that are just erupting lava flows. And you can see that if you have a basalt, you'll get these kind of Hawaiian-style effusive eruptions, and it's low viscosity, so it can flow a very long way. And this means that you get long, thin layers, and this produces kind of like a shield volcano shape, right? If we have an andesite, it's more viscous, so it's not going to flow quite as far. The lava flows are going to be thicker, and we're going to get more of a doming shape. And then with a rhyolite, they're really not going anywhere, so you might get like quite a steep-sided dome shape, if it's just effusive flows. Now, some of the volcano types that we're gonna talk about. This picture just has a bunch of them all to scale. So we've got shield volcanoes, and these are by far the biggest. So we already talked about Mauna Loa. It's 4 kilometers above sea level, another 5 below sea level, and you can see here it's probably 90 kilometers across or something. Absolutely enormous volcano. You can get smaller shield volcanoes, and then stratovolcanoes, and then down at the smaller side we have cinder cones. There's some other volcanic features that I'm going to talk about, including volcanic fissures, lava plateau, calderas, spatter cones, tuff rings, and Maars that are not shown on this, so we don't have the scale. So shield volcano, it's kind of just what we were talking about with the lava flows before. You have low viscosity basalt, you have high eruption rates. So essentially this can flow a long way and produce a nice gently sloped volcano. They're pretty typical of ocean islands, so these kind of plume-driven magmatism under the ocean. So Hawaiian shield stage volcanism is the most obvious, and it's kind of like, it's probably like the type locality for these shield volcanoes. Basically made up of a big stack of lava flows. They might be 1 to 10 meters thick, and it's got quite a gentle slope, 5 to 10 degrees. With these, actually, they tend to be gentler nearer the volcano, and then they actually get steeper off into the ocean, because once you start erupting into the ocean, it produces more like pillow basalt. It's the flows aren't able to go as far. Oh, yeah, I was wrong with Mauna Loa. 180 kilometers wide at the base, so it's even bigger than I thought. Yeah, here's just a picture of Mauna Loa that I've shown before. You tend to have a circular central vent, but there'll also be eruptions out of the flanks where magma is migrating away to the sides of the volcano and then erupting there as well. Where we have rifting, so this is either a mid-ocean ridge or in, say, a continental rift, continental flood basalt setting, we don't tend to get these shield volcanoes, and you see more lava erupting from fissures. So at a mid-ocean ridge, you may have some kind of central volcano, but because everything is pillow basalt, the flows can't really flow out very far and make like a big shield volcano. On top of that, the oceanic crust is constantly being moved away from the site of melting, so you don't really get that kind of shape. The continental flood basalts, because they're usually forming in a continental rift, you get these thick lava plateaus that are formed of composite Pahoehoe flows, and they're usually coming out of fissure vents. So this picture here is the Lahar fissures in Iceland, and this is the largest effusive eruption in history. It erupted 15 kilometer cubed of lava, which, just to put it in context, that's pretty close to the average amount of erupted material every year globally. So it's really big. And you can see this fissure just kind of carries on along, and all these lava flows have been sourced from these fissure vents. Spatter cones, these are kind of the products of a Hawaiian eruption, so you have a bit of a fire fountain. And the key thing here that distinguishes them from scoria cones is that they are welded lava. And so basically these little blobs are shooting up from a fire fountain, they're landing on the side, and they're kind of fusing onto what's already there. So you can have quite a steep-sided spatter cone. New eruptions can kind of erode a hole through down the side. So you can see this one from the Fagradalsfjall volcano in Iceland. There's a kind of round, fairly small spatter cone and a river of lava flowing out the side of it. And of course, we talked about cinder cones. These are from Strombolian, which are mildly explosive eruptions. And because the material is being thrown higher up into the air and it's not really making a lava flow, we're just getting these blocks of, these bombs of scoria. The slope of these is essentially determined by the angle of repose, like the maximum gradient that you can stack scoria in a pile. So they're never steeper than about 40-degree slope, and this is the same scoria cone that I've shown you before from Haleakala in Hawaii. So by comparison, the spatter cones can be really, really steep, and they can be quite small in some cases, depending on the size of the vent and how much lava is flowing out of it. The next type, and these are formed from explosive eruptions, are stratovolcanoes. They're sometimes called composite volcanoes because they're a composite of lava flows and explosive eruption deposits. So you see these in more viscous magmas, typically andesite to rhyolite, and it has to be capable of explosive eruptions. So near the summit, you have very steep slopes, and that's because you have these high viscosity lava flows coming down the side, and on top of that, you have some sort of pyroclastic deposits, of volcaniclastic deposits. The lower slopes, the lava flows aren't making it all the way down because they're viscous, they can't flow very far. And so the lower slopes are just tephra volcaniclastic deposits or material that's eroded from higher up in the volcano. So these are the opposite of shield volcanoes. They're steep near the middle and then they shallow out towards the edges. Mount Fuji is kind of a classic example of this, and it's really, really beautifully shaped volcano. Craters and calderas. So I put up this GIF because the Kilauea is erupting again, and the lava lake is pretty active as of the last few days. So this is a 24-hour time lapse of Kilauea crater. The USGS actually has webcams on the summit, on the crater there, so you can just watch this anytime. I think they update about once an hour. So craters and calderas are both circular depressions formed by eruptions, and they're just distinguished based on the size. So craters are fairly small, calderas can be massive. The Yellowstone crater is about 65 kilometers. Sorry, the Yellowstone caldera is about 65 kilometers across. Most of these different types of volcanoes, stratovolcanoes, cinder cones, shield volcanoes, have craters at their summit. And these are major vents through which the eruptions are happening. In stratovolcanoes and cinder cones, the crater shape is basically driven by explosive eruptions, so you get this kind of cone-shaped thing. Shield volcano craters tend to form because of subsidence after an eruption, and I think I have don't actually have a picture of it here, but the how full they are with magma in the case of Kilauea, where there's a lava lake, that height actually goes up and down depending on the eruptions that are happening at the time. So when I was in Hawaii in 2018, a great tragedy was that there'd just been a huge flank eruption, and basically that drained all of the magma out from underneath the central vent, and the lava lake wasn't there. It was totally dried up. Since 2018, it's been filling up again, and the height has severely increased after 2021, so it's really full. You can see all this cool lava at the surface. Often in stratovolcanoes, it's not just like a simple crater. There will often be growing lava domes inside it. So this is a picture of a crater, and you can sort of see the shape of it here. This side is partly gone, and then there's a big lava dome growing in the center and degassing. This plume is just volcanic gas. All right, so calderas form after large, so either Plinian or ultra-Plinian eruptions, and basically what happens is the magma chamber is overpressured at first and it drives this eruption. As you evacuate all this magma and you degas load, the magma chamber pressure drops and drops and drops, and it becomes partially empty. And then the roof might become unstable and collapse in. And if the roof collapses in, you get this kind of big circular depression, and you get these things called ring faults at the side, where the roof has basically slid down through. They often end up filled with lakes afterwards because they're pretty low. And you've actually seen one of these in Spain. So this was the Rodalquilar caldera, and this was, I think it was something like 10 kilometers across. It's quite a big caldera. And in this photo, this is the gold mine that we went to. Essentially, all this flat area in the middle is caldera. Often, these calderas are associated with economic mineral deposits because you have this magma chamber, and the caldera collapse gives you these kind of nice pathways for fluids to travel through and remobilize metals, and that's essentially what's happened in Rodalquilar. The gold deposits, this is just kind of a generic picture of what kind of deposits you can form in a caldera, but Rodalquilar is at the edge of the caldera, and the gold deposits are epithermal gold that have traveled up some of the ring faults at the edge of the caldera. Okay, I think this is the last landform we're going to look at, and these are Maars and tuff cones. So phreatomagmatic or phreatic eruptions can produce Maars. They're basically these, imagine like an inverted carrot going down into the crust, and they often end up filled in by lakes. This happens because of that process of phreatomagmatic eruption, where we have magma coming up, it hits the groundwater, it explodes, and it basically blows a hole like downwards. This photo that I'd shown you before from Hunga Tonga is one of these type of eruptions. It was a phreatomagmatic eruption, and around the Maar you get this thing called a tuff cone, which is basically just like a gently sloping cone of phreatomagmatic tephra ejected by the eruption. Okay, so we get a huge range of volcano morphologies depending on the magma type and style of eruption. Effusive basalts will give us shield volcanoes or lava plateau, basically depending on whether we're an ocean island or a continental flood basalt. And they erupt either from fissure vents, crater vents, or spatter cones. Strombolian eruptions produce scoria cones, we've covered that already. And more explosive eruptions produce stratovolcanoes or composite volcanoes formed of this alternating lava and volcanoclastic rocks. If the eruption is big enough and the magma chamber is evacuated, then you'll get a caldera formation by the magma chamber roof collapsing. Phreatomagmatic eruptions tend to produce Maars surrounded by tuff cones. Does anyone have any questions about that section? Go ahead.
The Caldera in Spain,
Yep.
With the gold mine,
Mm-hmm.
how long time is it since that volcano?
I think, I don't quite remember, it's something like 10 or 12 million years. It's similar age to a lot of the magmatism around there. Yeah.
So it's millions of years
Yep.
to move something with the water.
In terms of the gold,
In terms of the gold,
I don't know how long the gold has been there, right? So probably most of it was happening when there was still magma in the chamber.
Okay.
So probably after the calderas formed, but shortly after, everything's still hot and you've still got tons of hydrothermal circulation. Yeah. All right, and then we're going to kind of wrap it all up by talking about the links between tectonics and volcanic style and volcano morphology. So this puts together some of the stuff we talked about on the more petrology, geochemistry side of things, and what that ends up looking like in terms of volcanoes. So mid-ocean ridges was the one we started with. So we've got rifting and adiabatic decompression, and the melting is able to continue to very shallow depths because we've essentially got no lithosphere under the mid-ocean ridge. That means we can have quite high degrees of melting we can produce a lot of tholeiitic basalt. It's got low viscosity because it's a basalt, basically. Because the ridge is always moving apart and the plates are moving away from the ridge center, there is no existing crust interacting with the magmas, so we've got no way of producing silicic melts. You do actually get tiny amounts of it, but it's enough that small enough we can just ignore it. So if we have high degree melts and they're coming from depleted mantles, so they're low in volatiles, we're not going to have any sort of explosive eruption. This is kind of compounded by the fact that we're usually under a 1 to 2 kilometers water depth. So that all the pressure from that water above limits exsolution. We don't have a lot of bubbles involved. We have no sort of explosive eruption. And so we just get effusive pillow basalt eruptions. And here's a picture of a pillow basalt, although I've cheated a bit. This one's actually from Hawaii. And we also produce the oceanic crust from these cumulates that are forming beneath the ridge axis. So that's mid-ocean ridges. Ocean islands, where they're forming from a mantle plume beneath thick oceanic lithosphere. So we have higher temperatures, so we can have adiabatic decompression melting even though we're beneath thick lithosphere. But the melting gets cut off at some point when the plume hits the base of the lithosphere. So if we're in the middle of the plume, we can be producing tholeiitic basalts and lots of them. But if we're towards the edges, we might be getting more alkaline compositions. So yeah, also if you have a slightly less strong plume, like lower temperature, then you might not be getting a lot of tholeiitic basalt either. But both of these are low viscosity, so we don't have much ability for explosive eruptions. The volatile content will vary. That's depending on whether it's alkali or tholeiitic. The alkali basalts are lower degrees of melting, so they'll have a higher volatile content because the volatiles are incompatible elements. And then also there'll be variable amounts of water in the plume depending on whether we're tapping some primordial water or some sort of recycled volatiles from subduction. And then of course how much of the normal depleted mantle is getting incorporated and mixed into the plume. So from the tholeiitic volcanism we'll tend to get shield volcanoes, large amounts of low viscosity lava, and then for the alkaline stuff, we'll either get flows, and going back to the stages of volcanism in Hawaii, we have this pre-shield alkalic and the post-shield alkalic, and these tend to be more lava flows. And then in the very late stages where we're getting very small degree melts with lots of volatiles, we might get these scoria cones. For continental flood basalts, again it's a plume, but this is happening under a continent. So we have, again, higher temperatures, but continents, when a plume hits them, they tend to rift. So similar to the mid-ocean ridges, we can actually get adiabatic decompression to a much lower level. So if we have really high temperatures and shallow decompression, then we get an absolute shit ton of lava. So yeah, this ends up coming up into the crust and probably end up with this quite complicated plumbing system of dikes traveling upwards, stuff getting stuck in sills, maybe carrying on further up. And so we'll see this plumbing system both as dikes and as these layered mafic intrusions. This is a picture of Skaergård again. Because the basalts themselves are low viscosity and they're low in volatiles because they're very high degree melts, then we're going to get effusive eruptions. But because we've got rifting and because we have kind of low areas, we're not just building up gradually on top of a shield volcano. You'll end up with some sort of lava plateau, one of these flow fields that are made up of these composite pahoehoe flows. On the right here, you can see the Deccan traps and those stacked lava flows, and these tend to be erupted from fissure vents. Because we have a lot of basaltic magmatism and a lot of heat flow coming through the crust, we can actually melt the crust a bit, and you get something that's called like bimodal volcanism, where basically you get basalt and rhyolite, but you don't really see andesites in the way that you would in a subduction zone. Go ahead, Bastian.
I didn't understand why alkaline basalt was more volatile.
It's just because the volatiles are behaving as an incompatible element. So if you melt just a little bit, then the volatiles are a very high concentration. But then, so the first melt that's formed has a lot of volatiles in it. But then as you continue to melt that mantle, the mantle that's left behind has less and less volatiles in it. So the magma the magma gets diluted in volatiles the more melt you add to it. Right. Subduction zones. So this is basically like everything else. Like, you know, this a lot of the volcano morphologies and eruption types are most common in subduction zones. So we have fluid flux melting. So our starting melts are going to be either calc-alkaline basalts or island arc tholiites. More of the calc-alkaline basalt in continental subduction zones, more like an island arc tholiite in some of these island arcs where the crust is quite thin. There's loads of volatiles because we've got fluid flux melting. We have all these complex assimilation, fractional crystallization processes. There's lots of crustal melting, and that's particularly in continental arcs. And so we have the potential to produce a really wide range of magma compositions, going from these fairly mafic calc-alkaline or island arc tholiite basalts, maybe through to andesites, rhyolites, daceites, the whole shebang. And so we can see all sorts of volcano types because of that. So in the main arc, we'll often see stratovolcanoes. Again, Mount Fuji, that's a kind of classic arc stratovolcano. You might form big calderas. You can get scoria cones. In the back arc, you can get lava plateau or even pillow basalt if the back arc rifts enough that it's under a fair bit of water depth. So basically a bit of everything. Okay. So just to sum that up, the style of volcanoes and volcanic eruptions is closely tied to tectonic setting, and that's because of the differences in magma types, volatile content, and crustal structure that we see in these different settings. Mid-ocean ridges is basically continuous pillow basalt volcanism with oceanic crust forming underneath. Ocean islands tend to be big shield volcanoes with small scoria cones on top. Continental flood basalts will form these lava plateaus erupted from fissures, and subduction zones have everything. Big mess. So, yeah, does anyone have any questions about that? Go ahead.
So continue on Bastian's question, I think.
Yeah.
The lava flows, the alkaline lava flows, that's because the magma has been enriched in volatiles, or?
The scoria cones are because it's enriched in volatiles, but if you get a lava flow rather than a scoria cone, it'll be something to do with either it's got less volatiles or it's less viscous, so the volatiles are able to escape easily.
Volatiles like carbon dioxide that increases or that decreases viscosity.
So water tends to decrease viscosity, carbon dioxide tends to increase it. Yeah.
When we talk about volatiles, it's just water mostly, or?
When I talk about volatiles, it's everything, so water, carbon dioxide, and sulfur dioxide. But yeah, when we talk about the difference between the flows and the scoria cones, it could be to do with the amount of magmatism as well. If it's not a very high eruption rate, then you have more chance of getting these gas bubbles trapped in the vent, and then it goes pop. Because they're low volume lavas, they're more likely to have more volatiles, and so you've got more potential to make gas bubbles and have these strombolian eruptions. Yeah. All right. That was it for that lecture. So I think we can take 10 minutes and then meet back. 2:10.